Alright, in the previous class we have seen that quite unlike a gas laser or a solid state laser, a liquid laser such as the dye lasers have the capability to provide continuously tunable coherent light. In this class, let us try to gain an insight into the working of such a continuously tunable dye laser. A few low-lying energy levels have been shown here for both ground as well as excited electronic states of a dye molecule that participate in the lasing process. The two types of electronic states that a molecule can have are single and triplet states. They essentially play totally contrasting roles in the operation of the dye laser. The singlet and the triplet states of a system are basically categorized depending on the orientation of the spin of the electrons that make up the system. In a singlet state, the spins of the electrons are paired. This means that the electrons have opposite spins so that they cancel each other out. Therefore, the total spin now will be half minus half, 0. So the degeneracy of the level, which is expressed as 2s plus 1, therefore will be 2 into 0 plus 1 equal to 1. That is why this level is termed as a singlet energy state. In contrast, a triplet state, in a triplet state, in contrast, two electrons have parallel spins. So they are like that. Therefore, the total spin is now 1. So the degeneracy of the level in this case is 2s plus 1, that is 2 into 1 plus 1 equal to 3. That's why this is described as a triplet energy state. The ground state is usually singlet state, while the excited state that involves an excited electron can be either singlet or triplet. Now, this is the ladder of the singlet state. This is the ground singlet state, which is denoted as S0. This is the first excited singlet state denoted as S1. This is the second excited singlet state denoted as S2. And this is the triplet state ladder. This is the first excited triplet state denoted as T1. And this is the second excited triplet state denoted as T2. The ground state for the triplet state does not exist, as usually the ground state is always a singlet state. There are of course other triplet states and singlet states, but only those states, low-lying energy states, which participate in the process of lasing of a dye laser have been shown here. Now, in a liquid medium, these levels will be greatly broadened in energy, as they are composed of numerous rotational and vibrational levels. As you know, a dye molecule is made up of many atoms, and the liquid medium gives flexibility to all these atoms to simultaneously vibrate and rotate. Therefore, these are composed of numerous rotational or vibrational levels, giving it a band type of shape. Now, in the beginning, all the dye molecules will be residing in this state, and where? At the bottom of the singlet ground state, satisfying Boltzmann distribution at that temperature. If you of course increase the temperature, then gradually the levels which are above the vibrational levels will start getting populated. But most of the population in the beginning at a normal temperature would stay around the bottom of the singlet state, around here. Now, the pump wavelength must be chosen so as to interact with this group of molecules and transfer them close to the tip close to the top of the first excited single state. This is somewhere around here. This would allow, as we will soon see, to achieve the maximum tunability of the dye laser. And once excited to this point, the molecules will begin to quickly relax down the vibrational levels within this first excited singlet state. So as the molecules are excited here, they would quickly start relaxing within the vibrational levels located within this singlet excited state S1. Now, if this dye cell is placed inside an optical cavity, then before the excited molecule can decay appreciably down the vibrational levels, they are stimulated to drop back to S0. They are stimulated to drop back to S0 as their energy of excitation is used up to manufacture laser photons. Let me elaborate it a little. So, this is first excited singlet state, S1. Now, and this is the ground singlet state, S0. The molecules in the beginning are all residing at the bottom of this state. Now, as we have pumped, it has started relaxing down the vibrational levels in this excited singlet state, S1. Now, let us catch a molecule when it has come to this vibrational state. Although I am saying a molecule, there will be innumerable number of molecules which are here. Now, this molecule, because it is excited, it would obviously come down to a vibrational level. So this vibrational level of S0 by spontaneous emission. Suppose it emits a light of wavelength lambda 1. Another molecule will come down from this state to, say, to the next vibrational state, emitting a photon, spontaneously emitted photon at a wavelength lambda 2. Another molecule from here may actually come down to another vibrational level, emitting a third photon at a wavelength lambda 3. Although there would be many such levels and there will be many such spontaneous transitions emitting photons at different wavelengths. I am just showing 3 such emissions, 3 such transitions. Now, you have created gain in this medium. Now, if you place this medium inside a cavity comprises of a concave mirror, a partially transmitting output mirror, and this dye cell which contains this molecules which have now been excited, I place it here. So now, due to spontaneous emission, photons will be emitted at these three wavelengths. There will be other emissions also, but we are just considering this photons at these three wavelengths. So they have been emitted at these three wavelengths, lambda 1, lambda 2, lambda 3. And as it traverses through this medium, it will be amplified due to stimulated emission, because these photons have been emitted. We are taking those photons which has been emitted along the axis of this cavity. There will be emissions at other directions also. We are just ignoring them. Now, all this amplified light at these three wavelengths shine onto the output mirror, lambda 1, lambda 2, lambda 3. Now, suppose the output mirror rejects these wavelengths, lambda 2 and lambda 3. So, it just passes out, transmits, while it offers high reflectivity at lambda 1, say 95% reflectivity. And for this, the reflectivity is say 0. The mirror has been so designed, if possible. So then, only lambda 1, light at wavelength lambda 1 will be oscillating back and forth and will extract energy that is continuously being pumped towards maintaining population inversion. And therefore, this dye laser would laze at a wavelength which is lambda 1. And if suppose we design the cavity in such a way that it supports oscillation at lambda 2, so then lambda 1 will cease to exist, while lambda 1 and lambda 2 will cease to exist, while lambda 2 will now laze. Similarly, you can also choose lambda 3. You can, as a matter of fact, you can choose any wavelength. So then, as we said, that this allows to achieve maximum tunability. That is because if you take this, if you pump it right at the top of this first excited singlet state, then you can actually, there will be many vibrational levels from which spontaneous emission would occur and which will seed the stimulated emission. Therefore, it will offer much higher tunability. Instead, if your pump takes it just up to here, then there will be tunability only over because of this few vibrational levels. So probably you understand now why the pump wavelength is chosen to interact with the this group of population, transfer them close to the top of the first excited state, because it provides maximum tunability. So now let us see what are the challenges posed by these triplet states. You see, the proximity of triplet state T1 to the singlet excited state S1 poses a major challenge. That is because if this state and this state are energetically very close, then the molecules which are excited to this state actually can cross over to the triplet state before it can be stimulated to drop down to S0 and contribute to the lasing. And every time such an interstate crossing occurs, the pump energy is expended to produce, excitation is lost and is not realized as a laser photon, because the population has come here instead of undergoing stimulated emission and contributing to the process of lasing. This greatly lessens the effectiveness of a dye laser. And this crossover triggers two more ramifications. You see, T1 is essentially a metastable state. So the population that comes from S1 to T1 actually builds up here, accumulates here, at the expense of molecules that are available for continuing the lasing process. And in many dye molecule, the energy of the laser photons, that is this photons, matches with the energy difference between the second excited triplet state and this metastable triplet state 1. Therefore, the molecules at this metastable state can absorb the laser photon and be excited to T2, this is called triplet absorption. So basically the laser photon's energy matches with this energy difference, and therefore the molecule which has come here, it can just very well absorb this photon and climb up to the triplet state. So basically the dye molecule at the triplet state T1 absorbs these photons which is being emitted, this dye laser photon, and absorb it and climb up to the second excited triplet state. Therefore, populating the triplet state is equivalent to creating a laser photon sink within the cavity itself, detrimentally affecting the performance of the laser. So basically what you have, this is your one cavity mirror, this is the dye cell, and this is the output coupler, partially transparent mirror. Now this is equivalent, populating this state therefore becomes equivalent to as if you have put an absorbing cell here. So this is giving out photons and this is actually absorbing this photon. So this detrimentally affect the performance of the laser. So what is the remedy? A possible remedy from the harmful effect posed by the triplet state is to add a substance that is called quencher with the property of absorbing energy. When added to the dye, they are capable of removing the energy from the triplet level. So basically, this quencher Q, it can actually release the molecule from the triplet state and take out the energy, excitation energy, and release the molecule and bring it to the ground singlet state. So basically, the quencher would take out this extra energy, that is T1 minus S0 from this molecule. This molecule has this extra energy, this much energy. Quencher will take out this energy and release the molecule and make it appear here. And make it appear here. And that energy, quencher takes and it gets energically excited. So this releases the molecule back to the ground state S0 and facilitates the lasing process, because the molecule is now available to continue the process of lasing because of the quencher. Although quencher cannot stop system crossing, but its effect will be far less damaging in the presence of such a quenching agent, because the number of molecule which are now residing in the triplet state will be reduced, and therefore the absorption of the photons, intracavity absorption of the photon by this triplet state will be accordingly less, and this therefore it will improve the performance of the laser. How do you pump a dye laser? You know that in a gaseous medium the atoms and molecules are very widely separated. Therefore, it is not suitable for transverse pumping, because many photons will just escape through the gap and would not be absorbed by the light emitting molecules. In a liquid medium, the species are much tightly packed, and therefore active length of a dye laser can be very small because the species are very tightly packed. This makes pumping of the liquid medium, transverse pumping, possible for liquid medium, and pumping can be achieved either by a flash lamp or by another laser. And pumping is essentially affected by light of wavelength shorter than the operating wavelength of the laser. For example, this is your singlet ground state S0, and this is the singlet excited state S1. Now suppose you want a laser, dye laser, which should emit at a wavelength lambda 1, that is the lasing wavelength, lambda L. So your pump wavelength must be shorter than lambda 1. Only then lasing can occur, must be shorter than lambda L. So if you are pumping at a wavelength lambda pump, so lambda pump must be less than lambda L. Only then lasing can occur at lambda L. If your pump wavelength is more than lambda L, then the lasing cannot occur at lambda L. It would occur at a wavelength which is less than lambda L. So you can appreciate, therefore, pumping is essentially affected by light of wavelength shorter than the operating wavelength of the laser. As the flash lamp produces visible light over a wide range of wavelength, it is suitable for pumping multiple dyes. For example, you have two dyes. Say one dye, this is S0, this is S1. And for another dye, suppose this is S0 and this is S1. So you can see, for pumping this dye, lambda P1, and for pumping this dye, if we call it lambda P2, so lambda P1 must be less than lambda P2. So to pump different dye, you need pumping wavelength also as different. Now a flash lamp which produces visible light over a wide range of wavelength can be suitable for pumping multiple dyes which have different pumping wavelengths that can be derived from a flash lamp which provides light across a wide range of wavelength. And for better utilization of the pump photons, the flash lamp and the cell containing the dye solution is often enclosed inside a cylindrical reflector, because the flash lamp can emit light in various directions. So some of the lights which would not be absorbed by the dye cell in the beginning can be redirected by the reflective surface of this enclosure and put it back into the dye solution, which will enhance the pumping efficiency. In case of laser pumping, on the other hand, laser to be used is usually dye specific. For example, for this dye, you would need a laser whose wavelength should be say lambda P1, and to pump this dye, you should have a laser whose wavelength should be lambda P2. And same laser cannot give you both the pump wavelengths, unlike the flash lamp. So that is why for laser pumping, the laser to be used is usually dye specific. Nitrogen laser, copper vapor laser, argon ion laser, excimer laser, etc. often find use as a pump source for dye lasers. If a dye has to generate, say, wavelength tunable red light, it has to be essentially pumped by a green laser. So, if the dye gives tunable red output, then it has to be pumped by a wavelength which is shorter than this. Therefore, it can be pumped, say, by a green laser, green pump laser. A dye can typically provide tunability of wavelength of several tens of nanometers. Rhodamine 6G, offering approximately 80 nanometer tunability, appears to be the best. Tuning across a much wider range of wavelength thus calls for switching dyes and consequently pumping laser as well. For example, suppose we want a dye output, dye laser, which should offer, say, tunability over, say, 500 nanometer to 650 nanometer. Now, a single dye would not give you such wide tunability, which is about 150 nanometer, because as you saw, Rhodamine 6G offers the best tunability, but which is about 80 nanometer. So from a single dye, you cannot get such wide tunability. So you may probably need 3 dyes. So one dye give you 500 to 550 nanometer tunability. Then this is dye 1. Then the second dye probably gives you 550 to 600 nanometer. This is dye 2. And the third one gives you 600 to 650 nanometer, dye 3. So you need 3 different dyes to achieve this wide tunability. And for pumping each dye, you would need different pumping lasers as well. So how does the dye laser actually work? See, dye essentially is a long organic molecule, is dissolved in a solvent for its use as a liquid active medium. You have to dissolve it in a liquid. Often ethanol, methanol, toluene, benzene, acetone, or even water works as a good solvent. And the solution is enclosed in a tight cell so that the liquid does not leak out. For low power operation, it is not mandatory to flow the dye solution for heat dissipation. As you know, in the operation of any laser, the only a fraction of the light that is pumped in is emitted as the laser photon. Rest of the energy stays back into the system. It is eventually dissipated as heat and increases the temperature of the lasing medium. Therefore, for same thing happens for dye laser also. Heat also stays back into the dye medium, liquid medium, and heats up the temperature. However, for low power operation, it is not mandatory to flow the dye solution for dissipation of heat. Natural cooling will suffice. However, for operation at higher power, the dye solution is flown to remove waste heat by some cooling system, and it also prevents rapid dye degradation. As the dye laser is often pumped from the side, either by a flash lamp or by a laser, the dye cell wall must be transparent to allow the passage of pump light. In case of pumping with a laser, it is quite straightforward to guide the low divergent pump beam through the transparent dye cell. And pumping with a flash lamp, however, needs a reflective housing, as I said, to ensure better photon utilization. The cavity is usually formed by a concave output mirror and a diffraction grating in the litho mode. The underlying physics of the working of a diffraction grating, its operation in the litho mode, and one of its important variant, which is glazed grating, would be described while we study the operation of carbon dioxide laser, as these gratings find wide application in the operation of carbon dioxide laser. A beam expander, as you can see, is deliberately introduced between the dye cell and the grating and the diffraction grating to increase basically the area of the grating surface illuminated by the intracavity optical beam. This expands the beam area, therefore it increases the area of the grating surface illuminated by the intracavity optical beam. This enhances the resolving power of the grating, making it more effective as a tuning device, and also protects it from optical damage by reducing the intensity of the light seen by the grating. So then, you know how a dye laser operates, how you can get tunable output from a dye laser, although you cannot get very wide tunability from a dye laser. If you need wide tunability, then you will have to resort to using more than one dye, multiple dyes, and to pump each dye, if you pump them by laser, you need also different pumping lasers. So I think I would end here. So this brings to an end to our course on liquid lasers. Thank you.